He'll speak about geometry from Donaldson-Thomas invariants. Thank you, Tom. Up to you.
Thank you very much. Thank you for inviting me. It's really nice to talk to you all. I'm really sorry for the pre-prepared slides, but I didn't manage to sort out a tablet and work out how to use it. So this is the result. But please do shout out as many questions as you would like. I don't have any particular. I mean, I've shared the slides on the chat, but I'm really not intending to get through them all. So there's no real end I need to get to. So feel free to slow me down as much as you like. Somebody described this process is like projecting energy into a black hole. It is. So anyway, the more questions, the better. Okay, so I'm going to talk about this ongoing research program I've been working on for a while now, which is the basic aim is to try to use the Donaldson-Thomas invariants of some CY3 triangulated category to define a geometric structure on its space of stability conditions. So this CY3 category could be, for example, the derived category of coherent sheaves on a Calabi-Yau variety, or it might be a much simpler category defined by a quiver with potential. Okay, and why would you expect the DT invariants to be encoded like this? Well, yeah, I mean, there's not so many good reasons. Certainly a motivating analogy is the way that genus 0 Gromov-Witten invariants get encoded in a Frobenius structure. So that's a sort of analogy, a motivating analogy. The other thing is that in some examples you can compute these spaces of stability conditions, and you know that they do have interesting geometric structures on them. Okay, so the current status of this is that there's a nice conceptual framework which I'm going to sort of tell you about today, and there are quite a few interesting calculations where you take a particular example of a triangulated category and you can sort of understand what's going on. But there aren't any kind of general constructions yet. I don't know how to, generally define a geometric structure associated to a CY3 triangulated category. Okay, but maybe, I think once one understands the examples, then maybe it starts becoming a reasonable thing to try to prove general results. Okay, and this sentence probably won't make sense if you've never heard about this before, but this is what I'm going to try and explain, is that the main idea is that you should think of the DT invariants as defining Stokes data for some family of meromorphic connections which live on P1. And, so you get a family of such connections parameterized by the points of the space of stability conditions. And these connections don't take values in the group GLN or something like that. They take values in the group of Poisson automorphisms of C star to the n.
Where n is what?
Where n is the rank of the Grothendieck group. So this is really the algebraic torus with the character lattice equal to the Grothendieck group. Okay, so now you might object that the Grothendieck group may be infinite dimensional. Yes, but then you have to do something slightly ad hoc, I suppose. So in the case where your category comes from a quiver with potential, n will be the number of vertices of your quiver. If you try to apply this to the derived category of coherent sheaves on a threefold, then that n would be something like, the total cohomology of the threefold.
It's something like topological K-theory of your category.
Yeah, indeed.
Whatever it means.
Mm-hmm. But I mean, I should say that this is still quite a primitive subject. I mean, the most complicated example I understand is the A2 quiver, I suppose. Anyway, certainly the examples I know, n is just an obvious finite number giving the vertices of the quiver. And then I should say that the main analytic input, the main field of battle is some class of Riemann-Hilbert problems, which look for piecewise holomorphic maps from the complex plane into this C star to the n, which have discontinuities across certain rays. And the discontinuities are what's described by the DT invariants, and then you have to try and solve this Riemann-Hilbert problem. Okay, so we'll talk about this. Okay, so that's
the source, right?
Say again.
Rays in the source space of this map, right?
Yes, yeah, rays in C star coming out from the origin.
And I'm sorry, this group of Poisson automorphisms, it looks like it's discrete to me, or I know. I mean, does it have an algebraic structure or anything?
No.
Well, think of its Lie algebra, and I would think initially, I mean, think of that as Poisson vector fields on C star to the n. And if I thought about that as algebraic vector fields, then that would be a pretty reasonable thing, right? That would be an infinite dimensional Lie algebra, but it would basically just be functions on C star to the n, you know, regular functions on C star to the n.
Right.
But one,
will you have a group of global Poisson automorphisms, or it will be a
different.
kind of collection depending on sectors? Something
Yeah,
like
you know.
No. I'm just asking to. Yeah, I know, but I don't know Tom's framework.
So
I have my language for that.
Yes, we will discuss some of these things, although not in the depth that Jan and Maxime understand them.
Okay.
Let's get on to that, and you can certainly ask that question again later. Yeah, but certainly that's one of the main problems here, making good sense of that group. Okay, but let's discuss that a little bit later. And then I should say that very similar ideas, extremely similar ideas, appeared in the work of Gauto, Moore, and Knightsky, which is now 10 years ago. And you know, in physical terms, the label for what we're doing is the conformal limit of their story. They have very similar Riemann-Hilbert problems, but they are strictly different. The things they are doing are a little bit different. But nonetheless, many of the ideas are similar. Any more questions at this point? We'll get onto some specifics soon, and then maybe will be better questions. Okay, so if you've heard me talk about this before, let me just quickly summarize on this one slide what's new recently. So I've been doing some joint work with Ian Strawn, which gives a geometric description of what you should expect to get out of this Riemann-Hilbert problem, or one of the things you should get out. And it's a nice thing, it's a complex hyperkähler structure on the tangent bundle of the space of stability conditions. So I will explain this today and why you should expect that. So that's nice in that now at least there is a kind of respectable input into this program, which is DT theory, and this is a kind of respectable mathematical output. And now it's just the process in between, which is maybe still a bit experimental. The other thing I've been doing is solving these Riemann-Hilbert problems when you take the category of coherent sheaves on some non-compact Calabi-Yau threefold. And in fact, I need there to be no compact divisors. So really things like the resolved conifold, just where you just have kind of curves. And then this leads to, the interesting thing is that you get some, you solve this Riemann-Hilbert problem, you get some analytic function, and this analytic function has an asymptotic expansion, which is the same as the genus expansion in Gromov-Witten, for the Gromov-Witten invariants. But you know, there are many different functions which have a given asymptotic expansion, and this is some particular choice. Okay, so I know, I mean, some physicists have thought a little bit about this sort of thing, non-perturbative partition functions, and this is a nice example of how you could try to define them.
Yeah.
Is C cube is okay?
So again,
Three-dimensional complex vector space. C cube, it's Calabi-Yau, no compact divisors.
Yes, this is okay. Yes, absolutely. I mean, yeah.
Actually, I have a question. If you don't have compact divisor, does it mean that intersection form is trivial?
Yes, and that's exactly the point that I need. Yeah,
Yeah.
that's exactly the point. Yeah.
I see.
Because it means that the automorphisms associated to different rays all commute with each other, which makes solving the problem much easier. And then I've also been working on a solution to the problem for the A2 quiver. So in this case, the intersection form is non-zero. The Euler form is non-zero. So this is a sort of harder case. And you basically get a solution by studying, there's a certain linear system, or I think of it as a second order ordinary differential equation, which has been well studied for 50 years in connection with Panlev A1. I mean, basically it's isomonaronic deformations are controlled by Panlev A1. And so you study that, that system, look at the monodromy map for that system, and it gives you a solution to the A2 problem. And this is really close to what Garrett and Moore and Knightsky were doing. Again, it's not quite the same, but of course it's extremely close to the things that they were doing. And I'm sort of wanting to try to generalize this to all these classes of quivers you get from triangulated surfaces, but I don't understand all the details of that yet. Okay, so that's the kind of high level stuff, and we can start doing some genuine maths. Any other questions?
Oh, actually, I have a question. Are you aware that for compact Calabi threefold, this DT invariant should go something like exponents of square, so nothing is convergent?
Should DT invariance should go like what?
Exponent of square of charge. So this kind of non-naive way to make any analytic function.
I was aware that you wouldn't expect that the sums of the DT invariants should converge, you know, in the usual way, and I don't know what implications that has for geometric structures you expect from the space of stability conditions. I don't know whether you understand this.
No.
Okay, but I mean, certainly that's a good point. The examples I'm studying so far are extremely simple, as you will see. Already they lead to very rich mathematics, but from the point of view of DT theory, they're very simple. And so it's not reasonable to extrapolate to the case of compact CY3s, because there might be some very different phenomena. And one of the key things is that for a compact CY3, you expect the DT, apparently, physicists and Maxime tell us that the DT invariance will grow very rapidly as you look for classes in the Grothendieck group, which are bigger and bigger. Okay. Right. Okay, so here's the plan of the talk. So first, I'm going to explain this story about Stokes data in the case of a finite dimensional group, GLN. So this will just be, and this is a very classical story, and this is just a motivating analogy. Then I will talk briefly about the wall crossing formula in DT theory. And then putting these two things together will tell us what is the expected geometric structure on the space of stability conditions. And you know, this is sort of, at this point, this is a little bit heuristic, but then you can do precise calculations in examples and show that the heuristics are correct. So I will discuss, it would feel dishonest to not do one of these Riemann-Hilbert problems and explain how you solve it. So I'll talk about the A1 case. And I don't know, depending on how many questions, that's probably as far as I will get. But you can certainly look at the handout where I will talk about, where there's some slides on the geometric case, CY3s without compact divisors, and this A2 case that I just discussed. Okay.
By the way, when you say you shared them in chat, the slides, did it do it privately to somebody or to everyone? Because I don't think.
Is it because not everyone was here when I did it or something?
Actually, I don't have it. Yeah, so maybe I should do it again.
I mean, one easy thing you could do is just Google me and go to my homepage, and it's on. Oh, would that be okay? Or I can try.
Actually, the slides were shared with everyone, I think.
Ah, just people who came in later don't see it.
That's
Okay.
possible.
I think in the chat there's a reference, right?
In the chat, there is a PDF file, and I download it very easily.
Ah, okay, I got it.
Has everyone got it, or who wants it?
Yeah, there's a link. I think it's okay now. Yeah.
Okay, I'll carry on. But if you do get stuck, it's also on my homepage under talks. Right. So let's talk about this Stokes data in the finite dimensional setting. This may be familiar to many of you. And so in this setting, I'm going to take G to be GLN and its Lie algebra. And we're going to take the standard root decomposition. So H is the Cartan, which I'm taking to be diagonal matrices. And this GOD is off-diagonal matrices. And the root system is what I've written there. Okay, so I think everybody knows this. The reason I'm being slightly kind of careful about this is that later we're going to want to replace this Lie algebra by a different Lie algebra. This one we discussed briefly before. The Lie algebra will be vector fields, pass on vector fields on C star to the n. Okay, so all the features that we have in the finite dimensional setting we'll need to have in that infinite dimensional setting. That's what I'm doing. So the only non-standard thing is this G odd, I guess, the off-diagonal matrices. Okay. And then I'm going to consider a connection with an irregular singularity. So, in fact, I've written it as a differential equation. Of course, it's also a connection on a trivial G bundle on P1. So T is the coordinate on P1 or on C star. And I'm looking for maps into GLN satisfying this differential equation where U and V are constant matrices. Okay, and I want to take U to be diagonal and with distinct eigenvalues, and then V to be in this off-diagonal part. Okay. So where does this equation come from? The point is that it's basically the simplest type of equation with a irregular singularity. Okay, so normally when we're considering meromorphic connections, we think about regular singularities, which means that the connection matrix has simple poles. And then the solutions have kind of logarithmic behavior near those poles, and we're interested in the monodromy of the solutions as you go around a pole. But in this case, this isn't a regular singularity because the pole has order 2. Okay, and so that's what we're going to be interested in. And this is basically the simplest possible kind. And these assumptions on U and V are just sort of to simplify things a little bit. Okay. So when you have a connection like this with an irregular singularity, then it's not enough to consider the monodromy of the solutions. You also should think about something called Stokes behavior, or Stokes data. So I'm going to explain what that is. And the first part of it is very simple. It's a collection of rays, and it's just the rays spanned by the differences of the eigenvalues of U. Okay. So another way of thinking about that is that U is in the Cartan, H, and the roots are in the dual, and we just pair those together. So we're pairing U with all the roots and taking the rays spanned.
Tom.
Yes.
This connection, if it comes from quantum cohomology of some variety, there is some bilinear form and condition of skew symmetricity of U, of V, U.
Indeed, yes. So
why did you skip this condition?
Because it's you can very well consider this connection without that condition, and so there was no need at this point to impose it. But yes, one place that you get connections like this is from quantum cohomology, Frobenius manifolds, and there V will be skew symmetric. Okay. Hi, Alexi.
Yes, fine.
Fine. And one other comment to make, just the obvious comment that if V happens to be 0, then of course we can just solve this equation, and the solution is e to the minus u over t. Okay, so already you see different behavior to what you would in the regular case, because you have this kind of exponential growth or decay depending on which direction you're coming into the 0. So this equation is sort of the basic, the thing that's going to be important for the whole talk. So if you have any questions, please do ask. Okay, so I carry on. So the fundamental result about, well, I guess irregular singularities is that you get solutions in sectors with good asymptotics. So in this case, because the pole is of order 2 rather than higher order, the solutions are defined in half plane. Okay, so the statement is that if I take any half plane which is centered on a ray which is not a Stokes ray, then there's a unique solution with good asymptotics, as in define the condition there, in that half plane. So I think I drew a picture. So here's a ray R, which is not a Stokes ray. So the red things are the Stokes rays. This is a non-Stokes ray. There's a half plane centered on it. And you expect, well, there is a unique solution in that half plane with that property. Okay. And of course, where did that e to the u over t come from? It was the comment on the previous slide that when v equals 0, the solution is e to the minus u over t. Okay. So, yeah, this is a sort of fundamental existence result. And one way you can prove it is using the Laplace transform. Maybe that's a, I mean, yeah, if you really want to understand this, that's one way to try to prove it. Okay. And so now we can define the Stokes factors by comparing solutions in different half planes. So maybe I'll just carry on. So draw the pictures. So here's the Stokes rays again, the red things. So suppose I want to define the Stokes factor associated to the Stokes ray L. Then what I do is I take two small perturbations of that ray, and then I get solutions defined on the corresponding half planes, and then I compare those two solutions. There are two solutions to the same differential equation, so they differ by a constant matrix, and that matrix is S of L, the Stokes factor associated to that ray. Okay. And one thing that's actually very easy to prove, just kind of a two-line proof, is that this SL is not, it can't be any element of the group G. It's constrained to lie in a very small part of the group, namely the part you get by exponentiating the root spaces corresponding to that ray. Okay, so that's...
Tom, this S of L is independent of T, is it?
Yes, it's a constant matrix. It's just an element of GLN, yes, because it's gotten by comparing two solutions to the same differential equation. So it's just a constant matrix. Yeah. And if you remember that these solutions, when you times them by e to the u over t, they tend to 1, that will tell you that SL, when conjugated by e to the u over t, tends to 1 as t goes to 0. And that will immediately tell you, if you think about it, that SL has to lie in some small part of the group G. Okay. So, I mean, generically, if U is generic, then these Stokes rays, there is one for each root of the Lie algebra, because all those U of alphas will be different rays. And so each of these, in this direct sum, that will just be a one-dimensional space. But for non-generic U, some of these rays can coincide, and then that thing inside the exponential could be a larger part of the Lie algebra. And then S of L could be a more complicated thing. I mean, it's not essential. But in particular, one of the things that you note from this is that it looks like there's a lot of data here, because it looks like we have an element of GLN for each of these rays. But in fact, there is the same amount of data in all this Stokes data and in the matrix V, because they're both basically parameterized by an element of G odd, okay? The sum of the root spaces. So I hope that's clear. So the thing you need to know is that when you have an irregular singularity, there are solutions defined on sectors, in this case on half planes. And when you cross one of the Stokes rays, these solutions jump, and the Stokes factors are the things which can, you know, tell you how the solution has changed. So it's, yeah, maybe that's enough. Any questions? So now we talk a little bit about isomonaronic deformations. So here's our differential equation again. And now what we want to do, yeah.
Can I ask about the previous slide?
Sure.
So you said that there is the same amount of data. Does this have some precise meaning?
I mean, suppose we fix the leading order term of the differential equation, which is U. Let's fix that. What do we need to do to specify the equation now? We need to specify that matrix V. And the way I set it up, V was just an element of G odd, right? The off diagonal part of the Lie algebra. So I could choose an arbitrary element of G odd. On the other hand, if we look at the Stokes data, these are exponentials of parts of G odd. And actually I can assemble the logarithms of the Stokes factors over all the rays, and I will get some element of G odd. So both the kind of monodromy, or rather Stokes data, and the equation itself are determined by elements of G odd. That's what I mean by the same amount of data.
But can you say reconstruct V from this collection of S of L?
Yeah, that's exactly yes, a very good question. So there is a map which sends V to the logarithm of all these SLs. That is a map from G odd to G odd. And that map is actually a local isomorphism of complex manifolds. Okay, so it's not a linear map, but it's, you know, it's a map from a complex vector space to a complex vector space, and it's a local isomorphism. And the question of reconstructing V from the logs of the SLs is a bit of a tricky one, but generically, indeed, it's possible.
But it is not one-to-one, is it?
It's not one-to-one because, I mean, it's very similar to the corresponding question for regular singularities, where I would map kind of the residues of my connection at a bunch of poles to the monodromy of my connection around those poles. And then you get into, I think it's Hilbert's 20-second problem or something, you know, can you come up with a connection with a specific, well, can you come up with a differential equation with a specified monodromy? And of course that question is, the answer is no. And that's because you've not really phrased the question correctly. You need to think about vector bundles with flat connections. And eventually you'll get to the Riemann-Hilbert correspondence, which is indeed an equivalence. And there is something similar here. If you consider connections with irregular singularities, you know, vector bundles with connections with irregular singularities, and some kind of Stokes, category of Stokes data, then you can make an irregular Riemann-Hilbert correspondence, and that will be an equivalence. So if you set everything up correctly, then yes, this map can be viewed as an isomorphism. But as I've set it up here, it really isn't. partly because I'm insisting my connections live on trivial vector bundles, for example.
Okay, thanks.
I hope that made some sense. It's sort of a complicated story, but it's exactly the same thing happens in the regular case, and is a sort of kind of famous piece of maths. It's worth it.
Yeah, actually, there was a guy in Russia who died, Bolly Bruch, he made a whole career about this.
Mm-hmm. Yeah.
Yep.
Okay, so here's our matrix differential equation. And so, I mean, Sasha's questions are extremely relevant to what I'm going to say next, because we just discussed the map. Yeah, so now what we want to try and achieve is that the Stokes factors are constant as we vary the leading term u. And it turns out that you can do that. So, and moreover, there is a kind of a unique way to deform the matrix V as a function of u so that these Stokes factors remain constant. I mean, and that more or less follows from what I just said about the map from V to the Stokes factors being a local isomorphism. Okay. And in fact, this condition that the Stokes factors are constant is equivalent to a partial differential equation for the variation of the matrix V as a function of u. Okay. So this maybe takes a little bit of unpacking. So yeah, what's the right thing to say? So what is this equation an equality of? It's G or G odd valued one forms on H reg. So we're thinking of the matrix V as a function of on H reg, and this is an equality of one forms, G valued one forms on H reg. Okay. I mean, the actual form of this equation is not too important, but it describes the way V varies so that the Stokes factors are constant.
And what's phi? Is a set of roots or something?
Yes, exactly. So I've just decomposed V into its roots according to the root decomposition. Yeah. So, so this thing is, and I mean, if you know about the Schlesinger equations, those are the analogous thing in the case of regular singularities. So in that setting, you have a connection with some singularities at some poles, and you want to know how to vary the residues of the connection as you move the poles so that the monodromy is constant. So in this setting, the pole doesn't move. There's only one pole or maybe two poles on P1, so it doesn't really make sense to move the poles. What you do instead is move the eigenvalues of the leading order term of your connection. And then see how the subleading term changes. And basically this whole story is almost the same as the story about semi-simple Frobenius manifolds. So if you have a solution to this equation over H reg, or over some open part of H reg, then generically that will give rise to a semi-simple Frobenius manifold. You need some other assumption like V has to be diagonalizable or something. So it's not quite correct, but it's basically the same. So the data of a solution to this equation is basically the same as a semi-simple Frobenius. And in that context, the eigenvalues of U are the canonical coordinates, so-called. So the canonical coordinates on the Frobenius manifold. So they give you the multiplication. And this V is telling you something about the Levitivity. Okay. So I think I'm nearly done on the finite dimensional setting. And yeah, there was one thing that I said there which was a bit too quick, because as U varies, these Stokes rays, of course, could cross, right? Because they are given by they're the spans of the differences of the eigenvalues of U. So it doesn't quite make sense to say that the Stokes factors should be constant in that setting. And the correct way to say it is as follows. So in this, it's best just to look at the diagram below. Those red rays are the Stokes rays again. And then we're worried that when we move, these red rays may collide. So what we do is we take some convex sector, and then we ask that the clockwise product over the rays in that sector of the Stokes factors should be constant. Okay, so this is a kind of slightly fancy way of saying that the Stokes factors should be constant. I mean, really what it means is that when two Stokes rays collide, you should multiply the two Stokes factors in the clockwise order. That's really what's going on here. But nonetheless, that's a nice way of saying it. And it's good to say it like that because that's exactly the form that the wall crossing formula takes in Donaldson-Thomas theory as formulated by Maxime and Jan. So if you think about how the Stokes factors now vary, they're kind of piecewise constant. So as the rays move around, the Stokes factors should be constant in one of these isomonaronic deformations, but sometimes the rays collide, and then of course the Stokes factors do change. So we'll see similar behavior for the DT invariants. Okay. And the last slide for the finite dimensional setting is, suppose we are given the Stokes factors as a function of u, and then we want to try and reconstruct v. Okay, we discussed this fact that v and the Stokes factors are kind of equivalent amounts of data. Can we actually reconstruct v? And the way you do that is you first try and construct these canonical half-plane solutions in this theorem of Bolsa, Jerkat, and Lutz. And then, of course, we can just differentiate those and get the matrix v back. And so how do you get these half-plane solutions? Well, this is where the Riemann-Hilbert problem comes from. It means that you should find for each non-Stokes ray the corresponding half-plane solution. And what properties do we know that these solutions have? Well, they have that asymptotic, they have that limiting behavior as t goes to 0. The connection that I wrote down actually had a regular singularity at t equals infinity. So the solution should have moderate growth as t goes to infinity. And if I take some, basically I'm just saying that here that the condition that if you compare these half-plane solutions for two different rays, then they should differ by the Stokes matrices. So this is just a sort of fancy way of saying that. Yeah. So you see, this is how you would go about, this is how you get back from the Stokes data to the half-plane solutions. You look for the from the Stokes data back to the differential equation. You look for half-plane solutions which have certain behavior at t goes to 0 and t goes to infinity, and which jump by the given Stokes data. And very roughly, you can see that that might give you a unique solution, because if you thought about two different solutions of this Riemann-Hilbert problem, they would differ by some matrix P of multiplication on the left by some matrix P of t, and that would be holomorphic. It wouldn't jump across the rays because both solutions jump in the same way, and it would have good asymptotics at 0 and infinity, so you might kind of think that P of t might be constant. It's not quite that simple, and as I was discussing before, even in this finite dimensional setting, the existence and uniqueness of solutions is quite a subtle thing. And it precisely relates to these questions about whether you should include vector bundles with non-trivial vector bundles and things like this. Okay. So that's the end of the finite dimensional setting. So are there any questions? The thing basically is, it's a shame that we all don't know the story a little bit better, is that when a connection has an irregular singularity instead of just monodromy, there are a bunch of rays emanating from the singularity, and there are matrices or elements of your group associated to each of these rays. Okay. And then you get interesting differential equations by asking for the Stokes data to be constant as you vary the leading term.
Do you see the metric already, or will it only appear later? I mean, yeah.
Well, I suppose what we're seeing here is, I mean, for example, this Riemann-Hilbert problem you would see exactly as stated here in Dubrovin's papers. So this would be some way of reconstructing a Frobenius manifold from the Stokes data of that Frobenius manifold. So, you know, there's some magic there. You know, for example, if I just give you the upper triangular matrix, you know, 3, 3, 3, 3 by 3 matrix with 3s up above the diagonal there, and you take that as your Stokes factors, then you will reconstruct the quantum cohomology of P2 like this. So certainly there is some magic here, but it's not the same as, it's not relevant to DT theory yet because the group is the wrong group.
But do you get like integral cohomology or rational or real? Because this looks like a complex story to me. Or
yeah, this is a complex story, but I would think of quantum cohomology of P2 as a complex manifold.
Ah, okay.
With yeah, with a family of connections on it.
Okay.
Pencil of connections on it. Yeah, I mean, I'm sorry, this stuff is just kind of unfamiliar to most people, and that's of course as it was to me. But it's a shame because this is, you know, this is a very classical story that's been known for, I guess, 50 years or something. Are there any other questions that might help? Okay.
Tom,
yeah.
Can I ask one thing about these Stokes vectors?
Mm-hmm.
So what exactly happens when, I mean, you explained that when two rays collide, then you replace two factors with one factor, which is just their product, right?
Yes.
But what happens when they move further? Now you need to decompose this one factor in a product of two other factors.
Yes.
But there may be, of course, you have the restriction that each of them belongs to the exponent of one root direction. But is it clear that this gives you a unique decomposition of that sort?
Yes, I mean, it is. Well, I mean, whether it's clear or not is true. I mean, it's because the Lie algebra decomposes as a sum of the Lie algebras. You know, this is nilpotent Lie algebras we're really thinking about here because we're just thinking about upper triangular matrices. And because you can decompose the Lie algebra of all upper triangulars into a sum of two things, then there's a corresponding decomposition on the level of groups. I suppose it's Baker-Campbell-Hausdorff.
Ungarer-Birkhoff-Hughes if you want. I mean, it's just.
Okay. Okay.
So what you're saying is true.
I guess it's in some neighborhood of the origin of the unit, right? Of the group.
Say again.
I mean, this uniqueness of decomposition is probably in some neighborhood of the unit of the group.
Not because the groups are nilpotent, pro-nilpotent.
Yeah.
Okay.
Yeah, I mean, it's basically if you give me an upper triangular matrix and an ordering of the roots, then I can write it as a product. Ordering of the simple roots, then I can write it as a product in the required way, uniquely. Yeah, but I mean, absolutely, good question. Yeah, that's exactly what you have to do when two rays separate. You know, when two rays that are lying on top of each other separate. That's the calculation you have to do to work out what to label the rays by. Yeah. Okay, if there's no more questions, I'll carry on. Oh yeah, one thing about sharing my screen is that I have no idea what time it is. Ah, this is good. Okay. So, so now we're going to talk about Donaldson-Thomas theory a bit, but I'm not actually going to tell you anything about Donaldson-Thomas invariants, I'm afraid. That's an old story. First, stability conditions. So I'm going to take some triangulated category, and I'm going to make this assumption that the Grothendieck group is free of finite rank. If not, take a map from the Grothendieck group, take a group homomorphism from K0 to such a group, and we'll do, you can do similar things. But let's just make that assumption for simplicity. And then there is this thing, the space of stability conditions. It's a complex manifold, and it parameterizes stability conditions, which are pairs consisting of Z, a group homomorphism from gamma to C, from the Grothendieck group to C. That's called the central charge. And also a full subcategory of D, which is graded by the real numbers. And so for each phase phi, it's usually called a phase, for each real number phi, there is a full subcategory P of phi, which whose objects are called semi-stable of phase phi. And there is some collection of axioms, which I'm afraid I'm not going to give. Okay. So, and the main thing you need to know for the purposes of this talk is that deformations of stability conditions are just controlled by their central charge. So the forgetful map, which takes a stability condition and just remembers this group homomorphism Z, this map is a local isomorphism of complex manifolds. Okay. So,
and does this theorem has something to do with the fact that the map from V to the Stokes data is a local isomorphism?
No, not yet. No. I mean, no, I don't think so. I mean, Z here will be the analog of U in that previous part. But I don't think there is any analog of the space of stability conditions in that previous setting. I could easily be wrong. But no, it's not, no. I think what you said there wasn't right. Okay. And one of the things, of course, just to say something maybe obvious, so this is a map from a complex manifold to C to the N, but you shouldn't think at all that this map is onto. It certainly won't be onto. And you should also, in general, it's not going to be a covering space of its image. This will be a pretty complicated map, particularly in the CY3 case. Okay. And then if you're in a nice situation and you're able to rely on many clever people's work, then given a stability condition, you can define DT invariants, which, I mean, this is too vague to be really useful, but I mean, it's something to do with the Euler characteristic of the moduli stack of semi-stable objects of that class gamma. So in particular, if you're in the very lucky situation that the moduli stack of semi-stables is the same as the moduli stack of stables, and that is a smooth variety, then the DT invariant, at least up to sign, really is just the Euler characteristic of that variety. So, but in general, of course, these are hard things to define, and there's some big rich theory devoted to defining them. But I mean, actually, in the sorts of cases that I'm going to be trying to consider this Riemann-Hilbert problem, I mean, it's really not very hard to work out the DT invariance of the A2 quiver. You know, there are ways, quite low-tech ways of doing this, using counting points over finite fields, for example. And then the point is that when you fix a class in the Grothendieck group, there is some wall and chamber decomposition of the space of stability conditions. So the walls are real codimension 1 submanifolds. and the DT invariance constant in each chamber. Excuse me. And then what you really want to know is what happens when you cross from one chamber to the next chamber. And the point is that there is this beautiful thing, the wall crossing formula, which completely solves this problem. And it says, which means that if you know all these DT invariants at one point in stability space, then you can work out the invariants at all nearby points. And I guess in principle, at all points in the same connected component of the space of stability conditions. Okay, so I'm going to tell you what the wall crossing formula is in a minute.
Tom,
yes.
What is omega?
It's this. So there is some, I mean, I should have written DT there. It's a misprint. In that green box, that should just say DT. Thank you. But where did it come from? It's that there are kind of two systems of DT invariance here, which are just equivalent data, and one differs from the other by some kind of multiple cover formula, which is written on the bottom here. So So the reason that the omegas are useful is that they're very often integers, whereas the DT and the things that I'm labeling DT are not.
And why do you consider k squared? Is it just because it is 3 Calabi-Yau, or this 2 is 3 minus 1, or?
No, it's a little bit complicated. It's that, I mean, obviously that 1 over k squared the generating function would give you a di-logarithm. And it's to do with the fact that if you look at the generating function for the number of points in BGLN, so the group GLN, look at the classifying space BGLN, and look at the Poincare polynomial of that. So it's the generating function for those things would look like something like x to the n over q to the n minus 1, q to the n minus q, q to the n minus q to the n minus 1. Okay, there's some generating function for those things. And if you cleverly set q equals 1, there's a sort of slightly subtle limit, then you get this 1 over k squared coming out there. So I don't have a clearer way of saying that. Probably Maxime and Jan could tell you. But no, it comes out of DT theory. It's really in the heart of DT theory, that, and it comes out of this quantum dilogarithm, which is the DT invariance of the point.
Okay.
Okay, yeah, and so I just wanted to, before we go on to discuss the wall crossing formula, this stuff looks extremely dry. I just wanted to say that this space of stability conditions, although it has a very abstract definition, is not, you know, just a really abstract thing. In particular examples, it gives rise to interesting spaces. So I just wanted to quickly describe this theorem, which says that there are examples of CY3 triangulated categories where this space of stability conditions, when quotiented out by the group of autoequivalences, is a space of quadratic differentials, so for example. So parameterizing pairs consisting of a Riemann surface and a quadratic differential, meromorphic quadratic differential on it. Okay, so, you know, this space of stability conditions is not an impossibly abstract thing. It can give rise to concrete and interesting spaces. And in this example, it's also possible to compute the DT invariance, and they basically count finite length horizontal trajectories of this of the corresponding quadratic differential. Okay. So I mean, this is the sort of level. I mean, I would very much like to solve these Riemann-Hilbert problems associated to this DT theory. I mean, this would be a reasonable thing to try and do.
This CY3 category, does it have some geometric nature?
Yeah, good question. Yeah, so Ivan Smith proved that it can, at least it can be embedded in the Fukaya category of a threefold, of a CY3, non-compact CY3, which fibers over your surface. S, and it's basically, its equation is basically, let's see, u squared plus v squared plus w squared equals q of x. Right, so it's some kind of quadratic bundle over the surface, which degenerates at the zeros and the poles of your quadratic differential. Yeah, so you can use your quadratic differential to construct a Calabi-Yau threefold, a non-compact Calabi-Yau threefold, fibered over S, and this thing is supposed to be the Fukaya category of that.
I'm confused. So it depends on Q, right?
Yeah.
But
the threefold depends on Q as a complex Calabi-Yau threefold, but the Fukaya category only sees the symplectic, you know, it only sees that threefold as a symplectic manifold. So as Q changes, the Fukaya category doesn't actually change, even though the Calabi-Yau threefold does.
Ah, okay. You have prescribed order of poles, so the type of the variety doesn't change. Okay.
That's right. Yeah, exactly. So, is someone asking a question? Oh, no, maybe not. So,
yeah, so this thing is visibly homomorphically symplectic. So this is a general phenomenon, right?
Sorry, what's holomorphic symplectic?
That space of quadratic differentials, because I mean.
Yes.
Yeah.
Yes, that's right. Because we had this, the space of stability conditions is locally modeled on the dual of gamma. And gamma has a skew pairing on it, which is this, which is the Euler form of your category.
Right.
So indeed, these things are always at least complex. There are at least Poisson spaces. Yeah.
Oh, Tom, actually, I have a question. I think it should be some mirror dual non-compact Calabi-Yau threefold, maybe rigid, such that this category will be a perfect complex with compact support on it.
That would be great. Yeah, I never really understood this, but you're saying that this category also should have a B model description.
Yes, definitely, yeah.
Yes, I agree. I mean, do people not know that? I mean, I don't know this, but
I have to think, yeah, but it's in general the Hitchin system should be dual.
Yeah. Yeah, I mean,
no. This is the subcategory of the Fukaya. The Fukaya, of course, has an obvious B-model dual, but because you have a spectral curve and your Fukaya sits on the conic bundle ramified over the spectral curve.
Yeah, it's okay.
So it's easy to construct the dual, but so the subcategory, it's not obvious.
No, so I think it will be all compactly supported object also.
On what? On the curve which defines
no, on some three Calabi, on some another three Calabi-Yau, which is rigid.
Yeah.
Maybe.
I mean, I guess I don't even know how to do this in the AN case. I mean, I haven't really tried, but you know, like there are particular examples of these where I take the genus to be 0 and I just take one pole of order n, and that will give me the AN quiver. But I don't know what the mirror dual, what's the natural geometric space whose perfect, you know, category of perfect complexes is AN. Yeah, I don't know. Anyway, I should carry on. Right. Okay. So let me just now move towards stating what this wall crossing formula is. Okay, so just have to introduce some data. So I have to introduce this copy of C star to the n, some algebraic torus whose character lattice is gamma. So its characters are these are going to be denoted x gamma. And also I'm going to assume that my category from now on is CY3. And so that means that this Euler form that's defined is skew symmetric. And so this gives me an invariant Poisson structure on this torus. Okay, so which defined on characters is like so. So yes, so basically we have a copy of C star to the n with a Poisson structure on it. And just some small print here is that when it's convenient from now on, I might assume that this form is non-degenerate. And also there is some small subtlety in the story where in many ways it's not really this torus that's natural, but rather some torsa over it, which leads to some kind of signs coming into formulae. And this is dealt with, this is also to do with what's called quadratic refinements of the form gamma. And I'm just not, they're not going to be on the slides, and they should be, but let's just all agree to forget about these for the moment. Okay. And so now we want to talk about what Lie algebra and Lie group we're going to be thinking about. So it's going to be Poisson vector fields on this torus T. And just as before, we want to think about some decomposition of this Lie algebra. So, so what's the Cartan going to be now? It's going to be translation invariant vector fields on T. So that's a commutative subalgebra. And of course, I can just identify those with their value at the identity. So that's just going to be the tangent space to the torus.
Translations means multiplicative translation, right?
Yes, yes, yes. Thank you. Yeah, translation by the group action on the torus. Okay. And of course, the tangent space of the identity of that torus. I mean, the torus was Hom from gamma to C star, so the tangent space of the identity is just Homs from gamma to C. And of course, note that is where the central charge of a stability condition lives. Okay, so that's the Cartan subalgebra. And then the rest is going to be Hamiltonian vector fields. And so we can identify that with the Poisson algebra of algebraic functions on T, regular functions on T. So that's this analog of the off-diagonal part. It's just all regular functions on T. And the roots now is, it's not finitely many roots anymore. The roots are all non-zero elements of the lattice. And the root decomposition of a function is now just kind of like the Fourier expansion of that function.
Tom, alpha is gamma in the formula?
Thank you, it is, yes. Yeah. Okay.
So in this case, Cartan is finite dimensional, but the whole algebra is not, right?
That's right. So the algebra is infinite dimensional, but not too badly in that each root space is one dimensional, and the roots are just the lattice gamma, or minus the origin.
And how does the bracket look?
Well, I wrote it there because that's the Poisson. So the bracket of vector fields, of course, is the same as the bracket of the functions giving rise to. Sorry, the bracket of Hamiltonian vector fields is the same as the bracket of. You know what I mean. The map sending a function to its Hamiltonian vector field is a Poisson map, a Lie map. Okay. And
the Cartan action is also the natural one, right?
Yeah, so if I take an element theta, a map from gamma to C, and I pair it with x gamma, then I just do theta of gamma. I can evaluate theta on gamma and times it by x gamma. So it multiplies a character x gamma by theta evaluated on that gamma. Yeah, it's the natural thing. And of course, the crucial thing here is because it's an infinite dimensional Lie algebra, there's not a well-defined exponential map. That exponential map would send a vector field to its time one flow. Okay, and would give, in theory, should give me an automorphism of my space. But of course, that will not necessarily exist. And in any case, it's important to note that even if it did exist, there would still be problems here, because the dt generating functions are infinite things. They're actually infinite sums of characters. Okay, so they don't live in this Lie algebra. Even though this Lie algebra is infinite dimensional, it's not infinite dimensional enough. right? So the dt generating functions do not live here. They would live in some kind of completion, and the whole thing becomes difficult. And this is, one of the things that Jan and Maxime have been working on. There's a recent preprint of theirs on the archive. And there are lots of interesting things as to how to make this make good sense of this. And I'm not going to be talking about that. The discussion here is going to become a little bit heuristic. But to make up for that, there are specific examples where you can do rigorous, genuine maths, right? So, okay, so we use the heuristics to try and guess what structure should exist, and then we verify that in examples. Any other questions about this slide? Okay, so here's the dt automorphisms. So let's suppose we have some CY3 triangulated category and a stability condition. So then in theory we have dt invariants in good cases. And then to each ray in the complex plane, we're supposed to define an automorphism of my torus. So, an element of this group G. And so the way I do that, I'm going to say how it acts on characters by pullback. And it acts by this formula.
Sorry, Tom, what is G?
So G, I think slipped in on the last slide. G is the group associated to this Lie algebra. So it's the automorphisms of the Poisson automorphisms of the torus. However, so this is one, here, some work is required to make good sense of this. And I will discuss that in just a second. But you see, it's very similar to the formula we had before in the Stokes. One of the things we said about the Stokes factor associated to a ray is that it should be the exponential of the corresponding part of the Lie algebra. Okay, so that's what we're seeing here. And so, what are we doing here? In this first formula with the x, what's happening is that we're taking a sum of characters, we're thinking about that as a function on the torus, and then we're taking Poisson bracket of that, so that gives me an endomorphism of the algebra of functions, and exponentiating that will give me an automorphism of the algebra of functions. Okay, and there is a kind of a check to say that these two expressions that I've written down here are the same, an easy check, and you can do that. That just comes from that multiple cover formula. Okay, so I mean, in good situations, there are only finitely many non-zero omegas, or in simple situations, and then the thing on the right makes perfect sense. It's a birational automorphism of, it describes a birational automorphism of the torus. So I don't know how much sense this is making to people. So I'm writing down not so much an automorphism of the torus as an automorphism of the ring of functions of the torus. And I'm saying, what does it do to characters? Okay. And just imagine that only finitely many omegas are non-zero, then this makes perfect sense. It's the action of a birational map on the torus. Okay. So, but in general, you need to work hard to make some sense of this. So in certain situations, what you can do is, instead of looking at the automorphisms of Laurent polynomials, which are the functions on the torus, you can look at automorphisms of this completed ring of functions, completed polynomial ring. That's not, I mean, that's perfectly good for stating the wall crossing formula. That's enough. But for some of the things that we're going to want to do later, there's other things that you might do. You might work with birational automorphisms. That will be okay if only finitely many of the omega gammas are non-zero. Or you can use automorphisms which are defined on smaller open subsets, so just analytic open subsets. Anyway, so making sense of this is one of the problems.
But where do you complete? Do you complete at zero, or I mean?
Where in that first thing, formal growth. So what it corresponds to is that you see, if you're only interested in rays in one half plane, essentially that means that you're only interested in the gammas that are where all the entries are positive. So you know, so you're only interested in half the lattice. So if you think of your lattice gamma as z to the n,
Right.
instead of thinking about the group algebra of z to the n, think of the monoid algebra of n to the n, your natural numbers to the n, and then you can complete that. And so if you're just thinking about rays in some convex sector, then that's enough actually, because they will all live in that kind of monoid algebra, and you can complete it and everything works fine.
Right.
It's only if you're trying to think of rays and the opposite ray at the same time that things become really hard.
Okay.
And so here's the wall crossing formula that I explained before, or mentioned before, and it takes exactly the same form that we discussed before. So each ray, there is associated some automorphism of this torus. I mean, that should really be in inverted commas, as we've just been discussing. And the claim is that the product over clockwise ray, sorry, the clockwise product over rays in a sector is constant as I vary the stability condition. And so it basically means that as two rays collide, you need to take the product of the two Stokes factors, and when they separate, you need to do this procedure that we discussed a little bit before. And I mean, just one point is that my exposition may be making this look rather vague. I mean, people actually put this into a computer and compute DT invariants using it, right? So this is a very precise formula, which is perfectly, you know, there's nothing vague about this. I mean, in particular, if you work in a power series ring, you can compute these things order by order. And so people will put this into a computer and use it to calculate the DT invariants.
Tom, but is this product a finite product or is it infinite?
No, it's a finite product. Sorry, it's infinite. But if you worked in, as we were just discussing, instead of in, if you work in this power series ring, then order by order, it's finite. So if you're only interested in monomials of degree up to a certain number, then there are only finitely many rays. Did that not answer? I mean, there are infinitely many rays, but let me see. If you look at this sum dt gamma x to the x gamma, and you think of gamma, you know, that's really sort of x1 to the i1, x2 to the i2, and so on. If you kill all monomials of degree higher than 100, then there will only be finitely many rays which contribute. Okay, and then you can just increase 100. So order by order, this is a finite product. I don't know whether that answers.
Okay.
Indeed, there are, you know, it's a bit subtle. Okay, so that's the wall crossing formula. Yeah, I think I've discussed that. Right, so let's just do one example, and then. So in the A2 quiver case, our lattice is just spanned up.
Can you reconstruct the connection from these Stokes vectors?
Well, we haven't written down the connection yet, but that's basically what I'm trying to do. Yes. At the minute, I mean, so far we've just discussed, you know, we had the finite dimensional discussion of Stokes data. Now we're just discussing DT theory and the wall crossing formula. And we happen to have observed that the wall crossing formula looks like the iso-Stokes condition that we had before. And then in the next part, I will quickly put these together and see what we get. Yeah. So, but this is the last slide of this section. Let me just see what happens in the A2 case. So we take the A2 quiver, the Grothendieck group is rank 2, and the Euler form is like that. And so the torus we're talking about is c star squared, and its ring of functions is like that. And there are basically two types of stability condition. In other words, the space of stability conditions, at least on the abelian category, splits into two chambers separated by this blue wall. On one side, the central charges of the two simples, whose classes are gamma 1 and gamma 2. On one side, they're one way around, and on the other side, way around. And the only non-simple indecomposable object has class 1, 1. And so it's unstable on the left and stable on the right. And that means that the DT invariants are as written. So on the left, there's just 2 non-zeros, and on the right, there's 3 non-zeros. So this is the most basic example of wall crossing in DT theory. And what's the wall crossing formula say in this case? It says that the composition of 2 birational automorphisms of c star squared is equal to the composition of 3 of them. And these birational automorphisms are the ones that I've written there. And I think this identity is very basic in cluster theory, and you can think of it as a pentagon identity because it's 5 things in it. Okay. So you see here, I could work in the in the power series ring in the variables x1, x2, and I could expand everything. I could expand this thing down there in terms of power series x1 and x2, and everything would just be positive powers of x1, x2. And so that's the thing I could do in general. But in this case, I don't need to do that. I can actually work with birational automorphisms because there's only finitely many DT invariants. Okay.
Yeah.
So we want, yeah, okay. So let's try and put this together now. So hopefully the story, the way I've told it, it's now clear what we should do. I mean, we take some CY3 triangulated category, and we should take our Lie algebra to be this kind of vector fields on the torus, pass on vector fields. And then
Tom, I'm sorry, can I ask about the previous slide?
Yeah.
So all you explained before was about 3 Calabi-Yau categories, right? But the A2 quiver is not a 3 Calabi-Yau category.
Yes. So I think the best way to think about this is that there is a CY3 category which has a bounded T structure whose heart is equivalent to representations of the A2 quiver.
Just double it, right? With a shift.
Exactly, yeah. So it's often called the Ginzburg algebra of the A2 quiver.
But you probably need to choose some potential then?
There is no choice of potential because there are no cycles in the quiver.
But when you double the quiver, you get a cycle, right?
Yes, but you don't. That's not the standard. that's not the rule of the game. So usually you take a quiver and you write a potential on that quiver. Then you introduce the backwards arrows and you take the DG algebra associated to that. And,
so in other words, this is just the shifted cotangent bundle of this quiver, right? The category.
Yes, correct. Yeah, and so from the point of view of stability conditions, there is a chamber in the space of stability conditions where the heart of the stability condition is just the representations of the A2 quiver. And so when you're thinking about stability conditions in that region, you can't really tell whether you're in the derived category of the quiver or the Ginzburg algebra. There's a region which is identified. Okay. Okay, so the idea now is that we should think about what we did in the first part of the talk, but with a different Lie algebra. And what family of connections are we going to take? Well, before we had the leading term was some element of the Cartan, And so the obvious thing to put there is the central charge, because that is a map from gamma to C. So it is an element of the tangent space at the identity to the torus. And we can think of that as an invariant vector field. And then what we put in the second part of the connection is some Hamiltonian vector field, and that will be defined by some function on the torus. And so that's the analog of this matrix V we had before. And the point is, we don't know what that function f is. That's what we would like to know. It's implicitly defined by its Stokes data, by the Stokes data of this connection. And that Stokes data is the DT theory, the DT invariance. So we don't know what f is, but we'd like to get our hands on it. And, you know, f is at least morally, f is a regular function, regular algebraic function on the torus. And so we can split it into its Fourier components. That's its root decomposition. Of course, this is still very heuristic. I mean, we saw that the Lie algebra of regular functions is not really enough. Okay, and right, so that's the picture. We're expecting to see this family of connections like this over the space of stability conditions. Okay, so now we write down the isomonaronic equation. It's exactly as before. It's just kind of put in this Lie algebra. So instead of the bracket, we know what the bracket is in this Lie algebra, so it comes out like that. And now we're going to rewrite this, and this is where something interesting happens. So we introduce this function, and I call it the Joist function because Joist did indeed write it down. I'll say something about this in a minute. So this is a function on the tangent space to the space of stability conditions. So there are two local variables now. There's the central charge, which is the local data on the space of stability conditions. And then there's also coordinates on the tangent space, on the tangent fibers. But as we've discussed, I mean, the tangent space to the space of stability conditions is just given by maps from gamma to C, because they're just kind of deformations of the central charge. So this is a function on the total space of the tangent bundle to the space of stability conditions. Okay. And as you can see, it's really a function on the kind of quotient of the tangent space by a lattice. So it's really kind of a torus bundle over the space of stability conditions. This would be a function on. Okay.
Tom,
yes.
So stability condition is a pair, Z and P, right?
Mm-hmm.
In all your formulas, you have only Z and no P.
Yeah.
Is P somewhere hidden?
Well, yeah, that's sloppy of me, but I guess it's because we're discussing local properties, and locally the stability condition is determined by its central charge. But you're absolutely right. Everywhere I wrote Z, I should really write sigma, sigma being a stability condition. Yeah. But yeah, that's correct. Now, so if I translate the green equation, if I sort of see what that means for this Joist function J, I get some differential equation for J, which is this thing here. And it's sufficiently horrible that I've taken coordinates. So I took a basis in my lattice gamma, and now I can the local coordinates on the space of stability conditions are these zi's, the central charges of gamma I, and the local coordinates on the tangent fibers are theta I. Okay. And so you get this equation. And I wrote this down in a paper, and then in January, Ian Strawn wrote to me and said that this equation is well known, which was sort of what I was hoping would happen. So what I didn't hope for is that it had such a great name. So it's called the Lebansky's second heavenly equation. And it goes back to like the 70s. And once you know that, it's very easy to see that it's that equation is equivalent to the statement that that this expression here defines a hyperkalemetric, a complex hyperkalemetric on the tangent bundle. Okay, so
what's the symplectic form then?
What is the symplectic form?
Homomorphic symplectic form, yeah.
Do you mean the sort of the things yeah. So one of them, the characteristic property of these hyperkalemetrics is that omega minus, so the thing you get from J minus IK, one of those symplectic forms is pulled back from stab, from the base, from the space of stability conditions.
No, but it's non-degenerate.
Sorry?
It's supposed to be non-degenerate, if I remember correctly.
No, but the J minus IK one isn't. Maybe we should return to the. I write it on the next slide, I think. But what was yeah. So I should say what is a complex hyperkalemetric as well. I didn't really find this in tons of books or anything. So basically, but it's a complex manifold with a holomorphic, metric on it, and IJK, and satisfying all the same compatibility as you would in the usual definition of a real hyperkalemetric. But this is some just complex version of hyperkalemetric, but certainly which has been studied for a long time, since the 70s. Okay. So, I mean, yeah, so here's a little bit more information. So it's basically that you just need to write down these these vector fields on this tangent bundle to the space of stability conditions. So the VIs are just vertical things in the fibers, and the HIs go horizontal and some interesting amount of vertical. And in terms of that basis, I, J, and K are just these kind of constant block matrices, kind of Pauli matrices. Yeah, so that's that seems to be the natural structure you get out. And then afterwards, once I started rooting around in this literature, in fact, there's a paper by Mason and Newman in the late 1980s who basically explained that if you take kind of the isomonodromy equations and you put them in the Lie algebra of vector fields, then you get the equations for a hyperkalemetric. So what I'm explaining here was already known 30 years ago or something. I think the only thing that they hadn't, the thing that they didn't do is they didn't think about Stokes data of these. So they just took the isomonodromy equations and put them in a different Lie algebra, but they didn't think what form the Stokes data would then take in that Lie algebra. I guess there was no reason why they would. Okay, so in some ways this is an old story. Okay. And so so what I've done is I've defined something called the Joist structure, and it's basically just the same. It's the analog of a Frobenius structure when you replace this Lie algebra by the other Lie algebra. The point being, a Frobenius structure, as well as this family of connections, has various extra whistles and bells, like an Euler vector field and so on. And so in this case, something similar happens. So the main ingredient is the thing I've just been discussing, this complex hyperkale structure. And this was the thing I was trying to tell Dimitri, which is that if you define this omega minus form, which is the metric and J minus IK, so then this is a degenerate two form. And in fact, the claim is that it's pulled back from the base. Okay, so this is kind of the class of hyperkale structures that's of interest. I don't know whether these have been studied before. I mean, you see things called semi-flat metrics, where it's the metric that is kind of constant on the fibers. But here it's this omega minus.
Tom, what is small omega?
Sorry?
What is small omega?
Yes, it's some symplectic form on M, and it's actually just the inverse to the Euler form. So at this point, yeah, and thank you for the question, because I should have emphasized this. This whole thing is now actually assuming that the Euler form is non-degenerate. And that thing is the inverse to the Euler form, which defines a symplectic form on stab, on the space of stability.
So effectively, it's cotangent bundle, right?
Say again?
You say it's tangent bundle, but you might as well say that this is the cotangent bundle, right?
Yes, you might, yeah.
Okay, that's kind of more familiar.
And also to define a Joist structure, you need your complex manifold to have a holomorphic symplectic form, right?
Yes.
Uh-huh.
Yeah. Well, yeah. I mean, so yeah, as well as this metric, as well as this data, you also ask for some other things like an Euler vector field and periodicity and so on. Anyway, there is some complicated definition there, but the main and important ingredient is this hypercalar structure.
And where this definition can be found?
Yeah, so well, the thing on the hypercalar stuff I'm going to post after this talk. Actually, I was just so it should be on the archive tomorrow or the day after. But it's also on my homepage at the bottom. On the publications, you can find a paper with Ian Strawn explaining this stuff.
Just a quick question: is there any chance that the thing is equivariant with respect to this direction dilating the fibers of the tangent bundle?
I don't recognize that. No, I mean, there is a C star actually, which things are invariant under, but it's the Euler vector field Zi d by dzi. So rescaling the base coordinates, the zi's, which makes the thing invariant.
Okay. But there is some kind of interaction which makes it invariant, because that's much easier to classify. Okay.
Yeah, so in fact, we sort of classified these in that they're just completely described by a function satisfying that partial differential equation I gave before. But I don't know whether that's a nice description. Yeah.
Yeah, also, Tom, I have a question. In your example with quadratic differential, in fact, you have 1/2 of the space of stability conditions, yeah, the space of quadratic differentials, which is a base of Hitchin system. So then there is an honest hypercalar, not complex hypercalar manifold, which is not a part of the cotangent bundle to the space of stability conditions. Do you incorporate this kind of physical stability conditions, which are only 1/2 of the whole space?
It's a very good question, Jan. Yeah, thanks. Various aspects of that. So, yeah, so what Jan was saying is that, so the typical situation when you try to relate this to physics is that physicists are like these half-dimensional subspaces in the space of stability conditions, which are kind of related to Griffith's transversality. So for example, if you take the space of stability conditions on the Fukaya category of a CY3 fold, you expect it to include the moduli of complex structures on that threefold, but it will have twice the dimension of that. So the moduli of complex structures will be some half-dimensional space cut out inside it by Griffith's transversality, essentially. So, one question is, how do we see these half-dimensional subspaces? And this is very relevant to that, and I will say something about that on the next slide. In those quadratic differential situations, this half-dimensional space is just, say, fix a Riemann surface and consider quadratic differentials on that fixed Riemann surface. Then we get the Hitchin base, and then we get a genuine hyperkähler structure, real hyperkähler structure on the tangent bundle. So the interesting thing here is that we seem to be predicting that there is a complex hyperkähler structure on the tangent space to that space quad. And then the genuine kind of Hitchin space would be kind of half-dimensional in that. And I think that's correct, and that's something I want to try to prove. Yeah, but I don't know how to describe that complex hyperkähler structure nicely yet. But that's the prediction, that there is a kind of a complex hyperkähler manifold which is twice the dimension of the Hitchin moduli space. And it could be simpler. So the things are related by this kind of conformal limit process. And in fact, what people have found is that if you take the Hitchin moduli space and you apply this conformal limit, you get something called the semi-flat metric, which is essentially just comes down to special Kähler geometry. It's something quite simple. And I suspect the same will be true in this kind of bigger world where we don't, where we allow the Riemann surface to vary. So I'm sort of expecting that these complex hyperkähler structures I'm describing here are much simpler than these real ones.
So then you have a prepotential on your space, something like this function, which is, yeah, okay. Good.
Yeah. So let me yeah. So there's just one question here is
Tom.
Yeah, Sasha.
Sorry. So you mentioned this half-dimensional subvarieties in the modulus in the space of stability conditions.
Yes.
Do you have a description of this in case when this is derived category of coherent shapes?
No, I guess. No, I mean, I have a sort of, on the next slide, I'm going to say something about how you should be able to define those. But it would all be assuming that you could solve these Riemann-Hilbert problems and construct this, this Joist function J. I mean, given that, I think you should be able to say what these half-dimensional subspaces are. But we're a long way from doing any of that for the derived category of a compact Calabi-Yau threefold. I mean,
but do you expect some geometric meaning for these subvarieties?
I mean, so I don't know what you mean by geometric. I mean, of course.
I mean, in the Foucault case, you said that this is Griffith's transversality.
Right.
So is there something similar expected in the DB Koch case?
Well, in the DB Koch case, this half-dimensional subspace, it goes under the name of the stringy Kähler moduli space, and physicists more or less define it by saying that it's the moduli on the mirror, which is not very helpful for us. But no, I don't know how to see that half-dimensional, the stringy Kähler moduli space inside the space of stability conditions on the derived category. I don't know how to see that, no.
And what about the cases when the space of stability conditions is explicitly known?
Well, then you can see it. So for example, in these quadratic differentials situation, the half-dimensional subspaces are just the thing you get by fixing the Riemann surface and considering quadratic differentials on that fixed Riemann surface.
Yeah, you already explained that, but you didn't explain how to realize this category as stability conditions on DB Koch, right?
Right. Yeah. Well, I mean, for me, this is the same problem for any CY3 category. How do you see these half-dimensional subspaces? What,
I mean, maybe in the case of local P1 or something like this, is it possible?
To see what it is. I mean, yeah, I don't know. This is taking me. I mean, I think what happens is that in examples, you compute the space of stability conditions, and then you can see that there are these natural half-dimensional subspaces, but you have no categorical definition of what they are. I mean, you just, afterwards, you can see them.
Okay.
Okay, I mean, so this point was just to say that, I mean, the thing I'm trying to do at the minute is start with the Stokes data and come up with a Joist structure, or this Hyperkalemetric structure. That's analogous to starting with Stokes matrices and trying to define a semi-simple Frobenius manifold by solving this Riemann-Hilbert problem. Of course, the much more simple thing is to go in the opposite direction, starting with a Frobenius manifold, compute the Stokes data. Okay, so that's, I mean, I'm not saying that's an easy thing to do. It's probably a pretty hard thing to do, but at least all you need to say that it's well-defined process is this Bolsa-Jerkat-Lutz theorem. So really, that's probably what we should be thinking about doing, starting with this Joist structure. Now we understand exactly what this output data is. We should really be starting at that end and trying to see if we can define the Stokes data of such a thing. So I think if I was going to try and do something analytically rigorous here, I would try to go in that direction rather than going in the inverse map. Okay. And so this is just the thing I wanted to get to because it's relevant to what we've been discussing with this half-dimensional space and so on. So whenever I have a complex manifold with this Joist structure business on it, so M I'm thinking of as being the space of stability conditions, then we have this Hyperkalemetric structure. So that gives me a Leibniz connection on the tangent bundle of T of M. Remember that the Hyperkalemetric structure is living on T of M. It's not on M, it's on the tangent bundle, total space of the tangent bundle. But I can always embed M as the zero section inside T of M. And it turns out that this connection kind of preserves tangents to that. And so you actually do get a torsion-free and actually flat connection on the tangent bundle of M. And in coordinate, you know, in terms of that function J we had before, it's just given by this formula. Okay, and so I claim that the way to get these half-dimensional subspaces is just to look at flat submanifolds for this connection. Okay, so and you know, this isn't a vain hope. This is kind of backed up by calculations. So in the cases of these non-compact Calabi-Yau threefolds, like the resolved conifold, this really does give the right answer. And it also gives, in the case of the A2 quiver, it also gives the right answer. So I'm not quite clear what submanifold, which flat submanifolds you should take. So you have to, it's not quite clear to me what the correct definitions are, but in the examples, these are clearly, this connection clearly gives you the right answer. Yes, so I think this is relevant to this old problem. Okay, I think my time is nearly up, I would have thought. Yeah, so I've left you with a lot of slides to read. You're very welcome to. But I think it may make sense probably to stop here and take any further questions.
Can I ask a question then?
Sure.
So you mentioned these complex hyperkähler structures. Is there something like twistor spaces for them?
Aha, great question. Yes. Yeah, I mean, I find this whole business about complex hyperkähler structures a little bit strange. The literature is a little bit strange. Of course, you know, when you're talking about real hyperkähler structures, you just go and find the papers of Hitchin and everything is great. This complex analog, it doesn't seem to be, or at least it seems to have been covered by people who were mathematical physicists, maybe rather than pure mathematicians. So I have not actually found a treatment of twistor space for these things, but Dominic Joyce explained to me what you should do. But, and the way you do it is you, there are certain, when you have a complex hyperkähler structure, there are certain, you take combinations of I, J, and K. So you basically you look at AI plus BJ plus CK, where A squared plus B squared plus C squared equals 0. Okay, so that's a quadric in P2. So it's a P1. And each of those combinations has a half-dimensional kernel. So it's an operator on the tangent space and it has a half-dimensional kernel. So, and then what you're supposed to do is take the leaves of that, you know, so you've got a kind of half-dimensional space at each point, you've got a foliation, so you should take the leaves of that foliation. So that's what the twistor space is. It's fibered over this quadric, this P1, and the fiber over a given P1 is the set of leaves of that of the corresponding foliation. Now, I said all that just because that makes it quite hard to see whether it's a nice manifold or anything, right? You're taking some space of leaves of a foliation. And I think in the examples, what seems to happen is that there's one special point in P1, well, two special points in P1. Over one of those, the fiber of the twistor space should just be the space of stability conditions. It should just be M. And then I claim that over the generic point of P1, the fiber of the twistor space is basically the cluster variety. In these quiver examples, that thing is the cluster variety. Basically, yeah, I mean, it's hard to explain why that's the case, but already the cluster variety is a badly behaved thing. That's something we know about it, right? It's a sort of non-separated space. And yeah, so I would really like to understand that, the geometry of that twistor space better, but it seems, I think it's quite difficult. And it just doesn't seem to be addressed in the literature at all, this question about, you know, how can you form this leaf space and why is it a nice space and so on. So it's a very good question. I don't know how to.
And you mentioned there is a second special point on this P1.
Yeah, I mean.
What does it correspond to?
I mean, if I go back here, this is exactly the, so if we look at this HI and VI, and even this combination VI over T plus HI happening at the bottom. So basically I'm wanting to take the leaves. So T is my coordinate in the twistor, in the P1, essentially here. So I'm saying for T non-zero, I would think of the leaves of this thing as being something like the cluster variety. For T equals 0, it's probably something like N, because we're just going the vertical directions. And for T equals infinity, it's probably just the torus. So you're basically picking out the base or the fiber for T equals 0 and T equals infinity. And then in between, you're looking at sort of, yeah, solutions to the Riemann-Hilbert problem. Yeah, sorry, I'm finding this quite hard to explain, basically because I don't understand it well myself.
And is this foliation integrable?
Yes, that's part of that. Just follows from the fact that I, J, and K are covariantly constant for a connection.
Yeah.
And actually, sorry, the reason that your question is also extremely good is that if this Riemann-Hilbert problem, which I didn't really even get onto, but I mean, trying to solve this Riemann-Hilbert problem, what that is doing is calculating twistor lines in this space. So, I mean, yeah. So I suppose if one had a good understanding of this twistor space, then maybe you wouldn't have to go via all this Riemann-Hilbert problem business. Maybe you could just say, okay, I'm now going to look at the space of twistor lines, and that will be a complex Hyperkähler manifold, and it maps down to the space stability conditions, something like this, and you know, make all the analysis sort of implicit, because we know that finding the space of twistor lines is you know, actually writing down the equations is something difficult, but you can use Kodaira theory and things to show that they exist and that they move in a family of a certain dimension and so on. So I think if we could find a good understanding of that twistor space, that might be an alternative approach to all this.
Yeah, I have also a small question. In this Gayota-Murnetsky story, which you mentioned, they also have this hyperholomorphic line bundle, which actually holomorphic, you know, okay. What do you have it? Upgrade to hyper?
Yeah, that's a good question. I've forgotten how you define that thing. I mean, I remember them talking about it. I don't remember the definition though, I'm afraid.
It's basically related to the fact that there is quaternion Keller structure, not just hyperholomorphic and all that business. Yeah.
Okay. Yeah, I mean that was to do with framed BPS invariance as well, wasn't it? I mean, I imagine that the same thing would probably be true here because I'm taking very similar input to what they do. So I would imagine that the same construction will produce something. I don't know what it would be.
Kind of stupid general question. If you try to go back to flat connections, right? I mean, differential equations. Do you have a case that for what the fiber of this connection would actually be in this case? Would it be something like cyclic homology of the category or something?
You mean do you mean in the original case? I mean, so
no, let me put it like this: can you reduce your story some way to the original example of you know?
Yeah, I mean, I don't know whether you can do that or not. I mean, there is a mysterious. I mean, so the way I presented it, the first section was really just an analogy, and then we changed the gauge group. But I mean, it is true. It is true that in several cases, the space of stability conditions does have a Frobenius structure on it, and so it's kind of interesting to know to ask whether you could actually construct some family of connections for the gauge group GLN, but I don't know how to do that.
Oh,
yeah.
okay.
But Dimitri, I'd be very interested in your thoughts about these hyperkähler structures. I mean, I slightly wonder whether someone has studied them before.
It's too confusing for me. There's too much doubling going on. I have to think. But I mean, the prototypical example is always the Hitchin system, where you have kind of two ways to look at it. One, you can think of the part, like moduli space of flat connections on a Riemann surface, right? The simplest thing there is. So one way to look at it is that there is an open part there, which is just cotangent bundle to the moduli space of vector bundle.
Mm-hmm.
That's completely opposite way to look at it is to look at the projection to the Hitchin base. And then it looks sort of like the cotangent bundle of the Hitchin base, except it's not. The fibers are tori, not. So it's like a quotient lattice. So what you have here, to me, looks like it's similar to the second thing rather than the first one.
Yeah, but the dimension has been doubled, and that's the strange
Yeah,
thing.
but that might be an illusion. I mean, well, I don't know. I really have to think about it. But just to clarify, so you double the dimension, but do you take the quotient by the lattice? No. Or
Yeah,
yes.
yeah. I mean, yes. So here I presented it as a metric on T of stab, but there is a canonical lattice sitting inside that tangent space, and I can certainly quotient by that. I mean, we saw that when I wrote down the definition of this Joist function J. Although it did depend on the theta parameters, it really depended just on the exponential of the theta parameters. So it's really a function
effectively, it's like an integrable system again, right?
Yeah. So I mean, I think in the way you were just saying that, we can take the Hitchin base. So that's for example, quadratic differentials on some fixed Riemann surface, yeah. And then the Higgs bundle moduli space is an S1 to the n over that, right? It's some compact torus vibration over that.
Okay.
Jacobians, so S1 to the n. So what's going on here is we're taking the generic Hitchin base. So in other words, I'm allowing the Riemann surface to vary. So that doubles the dimension of the base. Now I'm taking quadratic differential and I vary the Riemann surface. And instead of an S1 to the n, I'm taking a C star to the n. So an algebraic torus instead of a compact torus, in other words.
Okay.
And so that's also doubled the dimension of the fibers. And so the claim is that there is a complex hyperkalemetric on that twice-dimensional space, which...
Okay, okay. I'll have to think. I mean, one remark which might be relevant is that when you have this integrable system, you typically only get it in one of the complex structures, so you shouldn't expect it to hold for the whole twistor family in any way, which kind of complicates things. So ideally, you would like to construct the whole twistor space as solution to some kind of moduli problem, but it's not clear what the model. I mean, it cannot be of this type. So the projection to the Hitchin base only happens over zero. So I don't know whether it helps or not, but
right. Yeah. Okay. I need to. I mean, as I say, I'm sort of. I think the next step is try to understand this geometric situation. Yeah, quadratic differentials, and see what happens there.
Right. And also an observation that I heard something like that also happens for quadratic differentials. Also happens in dynamics. People like Anton Zorich and other people.
Also happens what?
This effect, but
I'm a representative of dynamical systems.
For example.
Yeah. Definitely. This all counting. It will be counting of this brilliant lines. Yeah, actually, this was it's kind of for individual central charge, for individual stability condition. We have a picture with Jan, which is maybe will help it. Just to have a germ of holomorphic symplectic manifolds over disk, and we have non-linear symplectic connection outside of zero, and fiber at zero will be torus. It's kind of picture. So in real life examples, this fibers outside of zero will be some open part of character variety, and fiber at zero will be blown up. It will be torus. That's essentially it will blow up Hitchin system from fiber. Yeah.
And the symplectic connection doesn't go over the origin.
No, it just has its connection. I think it's this vector field 0 du or whatever variable used on the base, like Planck constant. You consider Euler vector field, then it leads to some actually non-singular vector field on a total space, and so on a torus it will be shifted by constant vector field corresponding to central charge. Yeah, so it's exactly similar to when you have this linear situation and you have second order pole of connection, then the vector field to T or ddt leaves the total space to completely clean.
But have you ever seen a space where the space of stability conditions is the central fiber and the general fiber is the cluster variety? Does that make any sense at all?
No. No, the central fiber will be this Lagrangian part of of stability conditions. So it looks like you should want to add something like one more dimension. Yeah, there was something. In fact, Nikita Nekrasov told me that it looks at in integrable systems which the total space is even dimension. Yeah, the base is like 2n and base of n. Then we can add n extra variable to get something like 3n dimensional. Yeah, which maybe is what here goes on.
Right. Yeah.
But can you really degenerate character variety to a torus?
No, the story is the following. You degenerate character varieties to the Hitchin modular space, yeah. But then on Hitchin modular space, you consider a fiber of Hitchin fibration, which will be a Abelian variety,
And in the total space, you make blow up in the center of the abelian variety. And then the exceptional divisor will be actually torus, analytically torus. It will be cotangent space to the abelian variety, which is holomorphically the same as the stuff of Morin.
But you do this after Riemann-Hilbert, so you don't do character variety, you do flat connections.
Yes, yes, yeah.
Okay. So it's not this W thing. It's not.
Sorry?
It's not related to P equal W thing, and you know. Okay. Okay.
No, the general story is that if you have this for given central charge, you can arrange the whole thing as deformation of a germ of some chain of CP1s and some codification of in some toric variety, and this germ will be a germ of a neighborhood on some codification of character variety. Yeah. And second role, using this exponents, you can add like blown up Hitchin fiber 0.
Okay. Okay. Thank you. All right. So if there are no more questions, are there more questions? Had enough. So let's thank Tom for great talk, and thank you very much.